Well, I want to talk a little bit about the natural log function with a few graphics to attempt to show a picture of the natural log function. Now, the natural logarithmic function is being pictured right here, and we'll get to that. The definition of the natural log function in calculus is that the ln x, ln the abbreviation for natural logarithm, is the integral from 1 to x of 1 divided by t with respect to t for x positive. The natural log function is only defined for x positive, so its domain, the set of all positive real numbers. Now, based on this definition, you can compute the derivative of the natural log function by using the second fundamental theorem of calculus. See, the second fundamental theorem of calculus says the derivative with respect to x of some function defined by an integral, where the variable is x and you're integrating from some constant to x, some function of t with respect to t. This derivative would just be, you place the t in this function definition here, function of t, with x. That's what you got up here. You get f of x. So the derivative with respect to x, the natural log of x, based on this definition, would be this 1 divided by t, replacing t with x. 1 divided by x. And then the animation, which I'm going to play for you again on the next slide, if y equals the natural log of x, then you can coordinate that with an area interpretation of the value of y, that the value of y is going to be negative the area picture when the area is red, and positive equal the area picture when the area is green. So, for example, this one here, we're at this point on the graph of the natural log of x. This is y equal natural log of x graph right here. And over here you got the graph of, in fact, 1 divided by x, or 1 divided by t. If this is going to be a t-axis. So if you're at this point in the graph of natural log of x, by definition, the y value there would be the integral from 1 out to the x value here, which in this case is 5, of 1 divided by t. Well, that would be the area under this blue curve between 1 and 5. That would be the value of the natural log of x for x equal to 5, and the picture in green. If x was actually back here, we're going to see the area pictured in red in just a moment. In fact, let's go ahead and do it. If x was this here, about 1/5, the y value would be the integral from 1 back to 1/5. Integrating in this function here, so integrating picture here, and the area picture here in red, if you compute that area, which in fact would be the integral from this 1/5 up to 1, which is negative the integral from 1 to 1/5. The actual value for your natural log of x for x equal to 1/5 is going to be negative. Here's the corresponding point on the graph of the natural log function, the natural log of 1/5. If I play the animation here, and what you can observe there is that the value of the natural log function changed from negative to positive as you move from one side to the other of x equal to 1. So if we click right here, the natural log of the x value right here looks like it's a little bit less than maybe 1 4/5. would be positive and would equal this area pictured here in green. If I move over here, the y value right here, which is the natural log of the x value right down here, is going to equal this area here pictured in green. If we look back here, we're going to have a case where natural log function value is going to be negative. If x was some number back here, this looks like it's around a half, maybe just less than a half, and by definition it'd be the integral from 1 back to say about a half, which is negative the integral from this number up to 1. And so the visual interpretation of the natural log of this number right here, value for x between 0 and 1, around a half, is just going to be a negative number. It's negative the area of this region here pictured in red. Kind of cool way of defining a natural log function, and it turns out to be the same function as you might have been familiar with in an algebra class, defined very differently. There's my animation again. As some examples, derivative with respect to x, the natural log of a times x using the chain rule would be 1 divided by ax, 1 divided by u, if ax is u, times the derivative with respect to x of your u, which would be ax here. Well, derivative of a times x is just going to be a, so you get 1 divided by ax times a, 1 divided by x. Kind of cute. The derivative of the natural log of ax is, as long as it makes sense, like a and x, a positive, x is positive, it's just the same as derivative of natural log of x. It's still 1 divided by x. You got a property, a natural log function, such a natural log of a times x is natural log of a plus natural log of x, as long as a and x are both positive. You can't you can't have one of them be negative there. Kind of an important thing to note. I think I'll underline that. That's really important there when you apply this property, that this a and x each have to be positive. But that being the case, if you differentiate natural log of a plus natural log of x, natural log of a being a constant, derivative is 0, and derivative of natural log of x 1 divided by x. So you're always going to get derivative of natural log of a times x equal 1 divided by x. Keeping in mind this stuff. Derivative of the natural log of the secant x plus tangent of x. Now again, that's going to be making sense if the secant x plus tangent of x is positive. By the chain rule again, it'll be 1 divided by this argument here, and times by the chain rule derivative of this stuff in here. Well, derivative of secant x is secant x times tangent x. Derivative of tangent x is secant squared x. Factor of secant x out of this stuff in parentheses, and you can divide out your secant x plus tangent x, just get secant of x. So derivative of natural log of secant x plus tangent of x just equals secant of x. It makes sense if secant x plus tangent of x is positive. You actually could get an antiderivative of secant of x by placing absolute value around this secant x plus tangent x. Derivative of the natural log of x to the 4th plus x squared would be 1 divided by x to the 4th plus x squared times the derivative of x to the 4th plus x squared, 4x cubed plus 2x. This does imply that the antiderivative, the whole family of them described here, of this function right here, which is this, would just be the natural log of x to the fourth plus x squared, plus a constant. X to the fourth plus x squared is going to be positive if x is positive, so we don't have to worry about absolute value around that. See, if you had something down here that could be negative, and then you need absolute value when you compute your constructed your antiderivative. As a general rule, if the derivative of the denominator of something equals the numerator, you can use your natural log function to integrate it. Good thing to know. Stay safe out there.